but it just takes longer.
Yeah.
So here we are. This is Wednesday, March 21st. So I figured section 2.8 should take an hour at the most to cover. This section 2.7 I covered in an hour and a half this morning in a class. So we'll just cover that tonight. I think we'll just do the 2.8 here and the review for test 3. There is in Shobi a review for test 3. So let's look at that real quick. Shobi. Okay, I have it set as 9 p.m. We will be doing some of this. We'll probably have about 2 hours to work. And unless you, so you don't have to get this all done before next time, but you should work on it. So because we're not going to have time to do every little bit in class, but I recommend that you do this, but I'm not going to collect this one. This is on your own that I did not collect, and it has the answers, and it's graphing a quadratic function. And we already did the section 2.2 homework worksheet. Oh, you can't see anything. I turned it on. Huh. Well, is it on? No. I don't remember if I heard it beep. There it goes. Sorry, guys. Hi, Brian.
I forgot, where your class was.
Oh, yeah.
So it was a trip.
Well, I'm just been talking and thinking I was displaying the thing.
What happened?
Well, that wasn't on. Now it's on.
I had a situation in class where it actually blew, it popped in class, and it was smoking, and we were panicking.
Oh, my. Okay, well, let's turn off the lights so you can see this. Okay, so what I'm saying, first off, I told the class that if anybody felt uncomfortable or heard the roads were getting bad, they can leave at any time. Fine. But we're just going to cover section 2.7 today. And 2.8 takes less than an hour. And then we'll review for the test next time. So we want to get out earlier tonight because the roads are bad, and so we're going to do that. And then I was showing you this in Shobi. This review for test 3 is due at 9 o'clock next Wednesday. But you shouldn't. We're going to work it in class, but I'm not sure we'll have time to work the whole thing in class. So maybe you should. So try to work what you can, maybe you can do these things. This is a recommendations for reviewing, and I said, this is going to be a 100-point classwork grade, but I don't want you to go and turn in this, the 2.2 on your own work. I just mentioned that that's a good thing to review and has the answers posted in D2L. And you've already turned in the 2.2 on homework, and this is like the 2.3 on your own. I have another one though. So it's already factored, so I'm asking you to find that. I do want you to do that one. Section 2.6 was due today, so you're not going to have to do it again, turn it in again. As I'm just mentioning, this is a good worksheet for what you need to be able to do on the test. Section 2.7 we're covering today. If you could work these, try to, otherwise I'll help you with those Wednesday. And another one. And 2.8, we haven't covered this yet, so you will have to wait till Wednesday to do that. Okay? So, that's all I'm saying here. You don't need to do these extra worksheets that I mentioned in this review by the time it's due. Okay. So we're going to do 2.7 today, and we have stretched this material out over a long period of time, so you definitely do need to be reviewing. Do the test review in my math lab. Don't wait till the last minute to do it. And if you haven't done all these sections in math lab, you should be done with those. And don't forget there's some quizzes there too, so make sure you do those. Get caught up in math lab. Don't wait till the last minute. So here's 2.7. So we've covered polynomial functions, and now we're going to cover and we've covered rational functions. Now we're going to cover polynomial and rational inequalities. And that's when you have the sign greater than, less than or equal, or greater than or equal. So this is the definition of polynomial inequality is any inequality that can be put into one of these forms. And the important thing about this is that if it's not set to 0, you want to set to 0. Okay? And then it says, so the next thing is we can use graphs to visualize the solutions of polynomial inequalities. So if this is our polynomial right here, and these are our polynomial inequality examples on the graph, less than 0 and greater than 0, we're going to first find the x-intercepts or zeros by we set f of x plus 10 equals 0, and then we factor, and it's an x and an x, and what are the factors of positive 10 that add up to negative 7? Minus 5 and minus 2, so it's minus 2 and minus 5. And then you set each factor to 0, x minus 2 equals 0, or x minus 5 equals 0. So you get x equals 2, or x equals 5. And those are those x-intercepts, 2 and 5, the x-coordinates of the x-intercepts, are called boundary points. And this is between where the graph lies above the x-axis, shown in blue. It says, well, let's see. Well, I have green here. If you're colorblind, you think this is blue, right? All right. I'll tell everybody. Well, you can't even tell, really. Okay, so above, where does the graph lie above the x-axis? That's for the greater than 0. That's in green here. And where the graph lies below the x-axis, shown in red. So this is going to be kind of a purplish red. This purple color here is for less than 0. Less than 0 is for below. See, this is y on the left side, where y is less than 0 is below the x-axis. and greater than 0 is where the function is above the x-axis, or positive. Y is positive above the x-axis. So if we were to find the solutions graphically to greater than 0, the solutions are the x values where this is true. It's important the solutions are x values. And we're going to write them in interval notation. So if I project the graph to the x-axis, it keeps going to positive infinity here, and because it's just greater than 0, it doesn't include the 5, the boundary point. And then I project this to the x-axis, it keeps going to negative infinity. And then we don't include the 2 because it says it doesn't have equal. So what are the solutions? The solutions are right here in green. I'll write it in interval notation, is minus infinity to 2, and we're not including the 2, so it's a parenthesis. It's always parentheses with minus infinity. Union with 5 to infinity. And that's the solution to greater than. Solution to that. And we found it graphically. So why did I not put the middle part in? Because it's an inequality and it's less than 0 it's below the x-axis in the middle part. But when we're finding domain, some people are leaving this middle part off. For domain, you'd keep the middle part. Well, domain of this is actually, this graph is actually all real numbers, but anyway, some people leave that middle part off for domain. I think this is where you're getting confused from. With inequalities, you want greater than 0 is only where the graph is above the x-axis or positive. So for a parabola, you do have a middle section missing if it's pointing upward. All right, and then what's the solution? If it's less than 0, you project that part of the graph to the x-axis, and it doesn't have an equal part, so it's 2 to 5. Those are the x values. It means the solutions are when x, this is what it means, x less than 5, greater than 2. That's what it means. That's interval notation, and the solution again is always in x values. So here's the steps for solving polynomial functions. We're going to express the inequality in the form f of x is less than 0, or f of x is greater than 0, where f is a polynomial function. And then, so we have to set it to 0. Set it to 0. Solve the equation f of x equals 0. The real solutions are the boundary points. We're going to do this in a minute. And we'll locate these boundary points on a number line, thereby dividing the number line into intervals. So the number line is dividing it into intervals. Choose one representative number called a test point within each interval and evaluate f at that number. And what happens, the boundary points are where the only place where it can change from being positive or above the x-axis to being below and vice versa. So we'll do a test point within each interval and evaluate f at that number. And it's important, don't choose boundary points as test points. Okay, and what happens is if the value of f is positive for that test point, then it means all of f of x is positive in that interval. And if the value of f is negative, then it means all of f of x is negative or below the left x-axis for all the x in that interval. And then you're going to write the solution set, selecting the interval or intervals that satisfy the given inequality. And so, of course, there's two other kinds of inequalities. There's the kinds that have the equal sign with it. So, if you replace less than with less than or equal and greater than with greater than or equal, the only change is that you must include the boundary points in the solution set. So you would use brackets for the boundary points instead of parentheses. So up here with the less than and greater than sign without an inequality, you use, for these, you use parentheses because for the boundary points, like I did up above, boundary points. Because it's greater than. But if we have f of x less than or equal to 0, these are the other cases. F of x greater than or equal to 0, you solve it the same way, you find boundary points, but now you use brackets. Because we're going to include the boundary point. All right, and now we're going to go ahead and do some examples. And it's going to make more sense when we do examples than when I tell you all this stuff. So, but that's a general procedure. You'll have to memorize this procedure. I don't give you this procedure on the test. I don't ask for steps. I don't tell you to find the boundary points and then choose test points. And I don't tell you these steps. Okay, so practice enough so that you can memorize it. So the first example here is we're going to solve and graph the solution set for 6x squared plus x greater than 1. Well, the first step is set it to 0. So we subtract 1 for both sides, and you get 6x squared plus x minus 1 is greater than 0. This part is our f of x. So we have an inequality of the form f of x is greater than 0. Okay? So what does the greater than sign mean? It means we're looking for positive numbers. Oh, I forgot. We're going to graph it first. A quick sketch. We're showing this method. 1. We're looking for positive numbers for test points. But okay, so our first step is to find the boundary points. After we get it set to 0, find the boundary points. The boundary points are the only place where it could possibly cross the x-axis and become, and the graph could be above or below, or vice versa. So you set f of x equal to 0. So 6x squared plus x minus 1 equals 0. Don't keep the inequality down here. You have to find the boundary points and figure it out first. Now, factor. And you only have an hour and a half to do this test, so you cannot use a quadratic formula for every factoring problem. You're supposed to know how to factor. If you don't, well, preliminary materials at the bottom of content where I have Hagen notes on how to factor. You may want to just print those out. There's little videos too of him telling you, going through it. But if you struggle with factoring, you may want to just print out the factoring notes, those little Hagen notes that he used to use. All right, but to factor, a trinomial factors into two binomials. So I put two sets of parentheses. One can only factor as 1 times negative 1. So we'll make this plus 1 and this minus 1. So the last term works. 1 times minus 1 is minus 1. Okay. And because this is 1, we're looking kind of for the factors of actually negative, because it's minus 1. We're looking for the factors of negative 6 that add up to x. But 1, the 1 here. Understood 1. 3 and 2, right. So we need 3 to be positive. So if we put 3x here, we'll be multiplying by negative, so we have to put it here. 3x and 2x. So we get, the first term works, we get 2x times 3x, 6x squared. The last term is minus 2x, and the middle term is 3x. And that's, if you combine those, you get positive 1x. So now that you factored it, you set each factor to 0. 2x plus 1 equals 0. Subtract the 1. 2x equals minus 1. Divide by 2. X equals minus a half. And set 3x minus 1 equals to 0. Add 1. 3x equals 1. And divide by 3. So x equals 1/3. These are the two boundary points. We're not including them because there's no equality sign up here. So I'll mark them here. Let's make this minus a half and this positive 1/3. And I'll put open circles on them because we're not including them here. And we're going to draw a sub n, or 6, the number in front of the x squared term is positive. So our parabola opens upward. A is 6, it's greater than 0. The parabola opens upward. And we don't care where the vertex is. We're good to just sketch a parabola there. Now, we're actually looking for positive or above the x-axis. So by using the sketch, we can see it's above the x-axis here and here. So we need to project that to the x-axis, project it so the solution is minus infinity to minus a half. And we're not including the boundary points because we don't have an equal part. Union with 1/3 to infinity. Those are our x values. And that's the quick sketch method. And then if you wanted to show this without the open circles but using parentheses, minus a half, 1/3, we'd have to put the parentheses like this. That's what it looks like. Any questions?
I have a question.
Yeah.
Why do we, so the right side, like greater than 0 is positive, so we would have to answer for the top part, right?
Yes.
And if it was negative, it would be under the
If it was less than 0, it would be between these two numbers.
Okay.
Yes, we project this part up. It's because it's greater than 0 that we looked at above the x-axis. This is x, the x-axis.
Okay.
All right, well, I'm really going to want you to use test points, but if you do, you could use, if you use a picture, you're going to make it kind of detailed like this. Because I always want you to show work. So showing work on these is showing the factoring and showing the boundary points. And then I usually use test points, but I'm not saying you can't do it this way, but you'd actually have to sketch a pretty good sketch. So we're going to show you the same thing using test points, test values. So these are the boundary points. I'm not going to redo all that work we did. We're using the same boundary points. So to use test points, first I'm going to write down what we had, 6x squared plus x minus 1 greater than 0. Those are the boundary points. And since it's greater than, we're going to put open circles. I like the open circles rather than the parentheses. Minus and a third. I like the open circles because you don't have to tell which way you're going with those. Now, on the quiz, concept vocabulary quiz, no matter if it's greater than or greater than or equal, they're filling in these circles, I think. So be careful of that. Maybe they didn't want to give it away. I don't know. MATLAB does not have it correct on how this is supposed to look. Like if it's open circles, I think they have them all filled in, which would include the value. So just you look at the inequality and draw your own picture. Don't rely on MATLAB's picture. Okay, so this breaks, these two boundary points break the x-axis up into 3 intervals, 1, 2, 3. And we'll write those intervals. So it's minus infinity to minus a half. Minus a half to a third, parentheses. Parentheses, a third to infinity. Those are the 3 intervals. So our solution could be any combination of these. We know what it is already. So to do test points, we're going to continue with dashed lines here. And we're going to pick some test points out. I'm just going to write test points. These are our x values that we're going to put in and test each of these intervals. Remember, each of these intervals is in terms of x. So these test points are x. Okay? They're x that we're going to plug in here and see what we get. And we're going to see what we get for f of x. And f of x is this part of it. Okay? And let's just write down that we're looking for positive values because of the greater than sign. And because there's no equal part, we're going to use regular parentheses. Okay, on the boundary points. So, our test points, don't ever pick, minus a half here. You want to pick a convenient number between minus infinity and minus a half. Do you want to pick minus 1,000? No, we'll just pick minus 1. So I'll just write it in this color. Minus 1. That's a convenient, just pick whole numbers if you can. All right, and then in this interval, you can pick 0. Anytime you can pick 0, go ahead and pick that one. In this interval, the first whole number is a 1. So we picked our test points. Now, we could put these in by hand, but you only have an hour and a half to do this test. So what I'm going to show you is how to use your calculator. You're going to use your calculator and you can put y1 equals 6x squared plus x minus 1. Then you're going to look at second table or second, well, the upper, it's table on the top of the key. So we're going to put these in. Clear. Did I cover up something you were writing? Okay. So y equals, and we're going to clear this out. And we're going to put in, you have to have 0 on the right. You're going to put in the left part, the left side. 6x squared plus x minus 1. Okay? And then let's check second table set. This is in ask mode, and I really want it to be in automatic mode. Automatic mode for independent variable, that's x. That means it's going to automatically give me a table of values. That was second window to set up the table. Second table. Okay, now I'm going to move it back over. So I got that function in there. At x equals minus 1, y, or f of x, is 4. So this is our value. If we had, and it wouldn't have been too hard on this one to put that in that function. Put negative 1 in for x, you're going to get 4 out, and that's positive. If you put in 0 for x, you get negative 1 out. I'm looking at the table to see these. And if you put in 1 for x, you get 6 out. Negative 1 is negative, and 6 is positive. So what are we looking for? We're looking for positive. So we don't want this one. We do want these. So this is the solution. And we write it with a union sign in the middle, like that. I'm not going to rewrite it. Okay, does that make any sense? We're going to do test points. So it lets you draw a detailed graph. And it's not a bad idea to click on graph and look at it to see if it makes sense. But sometimes the window can be tricky on those graphs. So test points, I'd really like to see test points. All right, so let's do some more, another example like that. This one's not a parabola. Next page. So this is to the third power. So again, you need to set it to 0 first. And these are not like terms. So you're just going to subtract an x from both sides and subtract a 3 from both sides. And then you're going to write it as x cubed plus 3x squared minus x minus 3 is less than or equal to 0. Okay? And now we're going to set this to 0 and factor it. Well, to save a step, I'm going to set it to 0 in the next step, but I want to start to factor to save a step. We're going to set it to 0 and factor. Anytime you have 4 terms, you should try factoring by grouping. Do you remember that? Okay. So you take your greatest common factor, the first 2, and these are all set up to work, by the way. All right. So you have x squared as the greatest common factor, and then you're left with x plus 3. You can distribute and make sure that works, and it does. And then factor, anytime you have a negative in front of the first term when you're factoring, you have to factor a negative out. And there's no common factors except the -1, and you need to factor the -1 out, the sign of every term. You can distribute and see that that works. -1 times x is -x. -1 times 3 is -3. Okay? So we factored and we have a binomial that's the same now. So we're going to pull the x plus 3 out. Think of dividing that out, and you pull it out and put it out front, and you're left with, if you divide by x plus 3 here, you're left with x squared. Divide this term by x plus 3, and you're left with -1. And that equals 0. Does that make sense? I had to show the other class this morning. They didn't. Sometimes people think we should have 2 copies of x plus 3 out there in front. So you could think of, you could rewrite this as if x squared, as if x plus 3 is a capital A. I mean, I don't know if you need to see this. X squared times capital A minus 1 times capital A. If you were factoring this out, you'd factor the A out, and you'd be left with x squared minus 1. Well, our A is just this binomial. So we can have factors, a common factor that's a binomial, and we can just pull it out. So you wouldn't have trouble with this, but sometimes people have trouble with that. And you can FOIL it and see if it, actually you would distribute to see if it made sense. X plus 3 times x squared is this term. X plus 3 times minus 1 is this term. So you have to distribute to see if that makes sense. If you FOILed it, you could end up with this. In some order. Any questions? All right. Now, does anybody know how this factors? You should memorize this, that, and I told you this before, it's a difference of perfect squares. A squared minus b squared always factors into a plus b times a minus b. That's the difference of perfect squares. So this is x squared minus 1 squared. So this 1 squared is 1. So this actually factors. We'll bring the x plus 3 down. So this factors into x plus 1, x minus 1. Now you're going to set each factor to 0. We have it totally factored. So x plus 3 equals 0. That means x equals -3. X plus 1 equals 0. That means x equals -1. and x minus 1 equals 0. That means x equals 1. These are the boundary points. So we're going to draw an axis over here and have these three boundary points. Here, let's put it in here. The next page has a line that I just copied. Anyway, okay, so you have -3, and then -1, and then 1. And I can write these ones like this. And we have a less than or equal sign. What is that? That means we're looking for negative, and we're going to include the boundary point. So we're going to use brackets. So we're going to we're going to include these, so I'll do it with a different color. So we're going to fill in these circles because we're including all three of these boundary points. So this breaks up, these three boundary points break up into the x-axis into 4 different intervals. So we'll write them down. -infinity to -3 square bracket. Square bracket -3 to -1, square bracket -1 to 1, square bracket, and 1 to infinity. Always use parentheses on the infinities because they're a concept, not a number. So that's the 4 intervals. We're going to have, some of those will be our solution set. Now we're going to find our test points. We're going to pick test points right here. So test points. So pick a number less than -3 that's convenient. How about -4? Between -1 and -3, how about -2? 0 falls in this interval, and let's use 2. Those are convenient test points. Those are our x values. We're picking them over here in the convenient numbers in each interval. And now we're going to find f of x. So we're going to type in our calculator that y1 equals all of this. And you may as well use it in this form in case you made mistakes factoring. I mean, it might be a good idea to make sure you factored right if you have time, by putting it in your calculator and seeing if the graphs are the same. But putting your factored form in and putting this in and see if it's the same. X, but I'm going to put x to the third, x caret 3, plus 3x squared minus x minus 3. You have to have minus signs between the terms, and if you had a negative sign somewhere, it'd be in front of the terms, but we don't. So we have to use subtraction signs there. Otherwise it'd be wrong. And then we're going to hit second table, second graph, this table. And we look at -4. At -4, we have a f of x of -15. That's negative. At -2, we have f of x is 3. That's positive. At 0, f of x is -3. That's negative. And at 2, we have f of x is 15. And that's positive. We're looking for a negative, so we want that one, but not that one. We want this one, but not that one. And we're done with the calculator. But you do make this table on your test because I can't see your calculator. And I expect you to show work. And so the solution is minus infinity to -3 square bracket union with square bracket minus 1 to 1. And those are the x values. This is the x-axis. Our solution is always the values of x that would make this inequality true.
So if there was no equal sign underneath that and it was still facing to the right-hand side, it'd be negative, correct?
If it was still facing the, you mean the big, if it's still a less than sign, this is a less than sign. But without the equal sign, you'd have parentheses here.
But it would still be, like, you would still be looking for the negative of it, right?
Yeah, yeah. If the sign's pointing the same way, which this is a less than sign, you look at the left part of the sign, it's the small part, so it's less than. Okay. All right. And that's how you do polynomial inequalities. But you do have to memorize that. All right. All right. So the second part is how do you solve rational inequalities? They're very similar. But let me remind you what rational numbers are. Rational numbers are when f of x equals p of x, an expression with x in it, a polynomial with x of it, and it divided by q of x. And for instance, it could where that's greater or equal to 0 or less than 0 or greater than 0 or less than or equal. So this is a polynomial. This is a polynomial. A rational inequality. These are solved the exact same way, except that you have to make sure one side is 0 still. The other side has to be a single quotient, a single fraction. And for the test, it's usually going to already be that way. And then the other difference, so one side has to be a single quotient, the other side's 0. The other difference is you have to set the numerator and the denominator equal to 0. You set them separately, equal to 0. And these are your boundary points. So you get boundary points by setting the numerator to 0 and boundary points by setting the denominator to 0. When you set the numerator to 0, those are the zeros. The denominator to 0, those will be the wholes or the vertical asymptotes. But it works the same way. You put those on a number line in order, and that divides the number line into intervals. Then you're going to choose one representative number called a test point within each interval and evaluate f at the number. This is still true, this part, A and B. If the value of f is positive, then f of x is greater than 0 for all numbers in that interval. If f is negative, then f of x is less than 0 for all numbers x in the interval. And then you're going to write the solution set selecting the interval or intervals that satisfy the given inequality. Okay, these steps work, so these steps are for f of x. Well, maybe, let me write this as less than 0, where f of x is irrational. F of x greater than 0. Oh, okay, sorry. So remember, these are rational inequalities, so it's actually p of x over q of x, but I just wrote f of x. So if you got a polynomial in the denominator, it's a rational inequality. You just set the numerator, denominator to 0. Those are the boundary points. Okay, once you get that, these steps work if the less than is replaced by greater than or equal, or the greater than is replaced by greater than or equal. However, this just means that you must include some boundary points in the solution set. Meaning you would use brackets instead of parentheses where the numerator equals 0. But never include the boundary points found when setting the denominator equal to 0. These are the vertical asymptotes or poles. So we don't, so I fixed the notes on this since last semester. The notes, I had to add all this in there. It's only going to be some boundary points. You can never divide by 0, so you got to still exclude where you set the denominator to 0. The values that would make the denominator equal to 0. All right, so we're going to do some examples. 2 of them. Okay, now, I don't know, maybe you guys can tell me if there's anything in Math Lab like this, but on the test, this will already be set up as a single fraction and 0 on the right. So, but I'm going to show you how to do this. You have to set it to 0, and you have to get a single fraction on the left. So we're going to subtract 1 from both sides. That you have to write as 2x over x plus 1 minus 1 greater than or equal to 0. Okay, now you need a common denominator to combine. We need to combine these into a single fraction. So we're going to rewrite 1. The common denominator is x plus 1. So we're going to rewrite 1 as x plus 1 over x plus 1. Okay. All right, and now you do need, around fraction bars, you do need parentheses. So so how you subtract fractions is you keep the denominator and subtract the numerators. So it's going to be 2x minus parentheses x plus 1 all over x plus 1. And now you're going to distribute the negative sign. So it's 2x minus x minus 1 all over x plus 1. be careful about sign errors. And this is 2x minus 1x is x. So we have x minus 1 over x plus 1 greater than or equal to 0. So this is how it has to be in order to solve it. Like I said, on the test it's already going to be set to 0 in a single quotient. So you won't have to do the steps I just did on the test.
Okay, you don't do anything with the 2x?
We did 2x, I combined like terms. 2x minus 1x is a 1x.
Oh, okay.
Okay? And now if you'd made a sign error here, you would have thought this was x plus 1 over x plus 1. And the whole thing would end up being 1. 1 is greater than or equal to 0. Why, that's always true. Now that's not a correct. So can you see if you made a sign error right there, you get an answer that wouldn't make any sense. Especially if you graph the original function. But for the test, you'll be given something like this that has a single quotient and 0 on the right already. Okay, so we're starting with, suppose we're starting with this. You look at this greater than or equal to 0 means that we're looking for positive and some brackets. So we're going to find the test points. So we set the numerator to 0. So x minus 1 equals 0. Add your 1, you get x equals 1. That's one boundary point. And do we include that? Can we include the 1? It's okay for the numerator to be 0. That's just 0. It's okay for the numerator. We can't divide by 0. So it's perfectly fine. Because of the equal part here, we're going to include this value, so we use brackets. Set the denominator equal to 0. X plus 1 equals 0. Subtract the 1. X equals negative 1. This, since nothing canceled here, this is a vertical asymptote. This is a VA at x equals minus 1. We never can include the vertical asymptotes. So we have to use parentheses. We don't include. We're going to use parentheses on this one. Okay, so these are our two boundary points. We need to make sure, remember to set, you're going to set these, you set these, the numerator to 0 and the denominator equal to 0 separately. Because of the equal sign, it's fine if the whole function ends up being 0. That's not undefined. But you can't divide by 0, so we're not going to include the number we got, the boundary point for setting it, the denominator to 0. But we do, so let's write these on the number line. Here's minus 1, and here's 1. Let's write it this way. Fancy. Okay, the minus 1 is a vertical asymptote, so we need to use an open circle there. The 1 is, when we set the numerator to 0, that's a 0. And it's fine for the graph does go through the 0. We'll fill in that with a closed circle. So that is fine. So that breaks up our x-axis into these intervals, minus infinity to minus 1, regular parenthesis, minus 1 to positive 1, square bracket 1 to infinity. So this is our x-axis. These are the three intervals that the boundary points separate the x-axis into. These are the only three places where the function can switch signs, or switch from being above the x-axis or below it. Okay. Any questions on that? We can also look at the graph when we're done. So we're going to find test points. So in this interval, minus 2 is a convenient test point. Between minus 1 and 1, 0 is a convenient point, and 2. Those are convenient points. Never use the boundary points. Those will be where it equals, well, either the denominator will equal 0 or the numerator will equal 0. Alright, now we're going to put this in our calculator. And for our calculator, we have to, I'm just going to write it this way because you're going to start with something like this. y1 equals, and don't forget the parentheses, x minus 1, close the parentheses, divided by x plus 1. If you leave the parentheses off, it's totally a different function. So you have to have, the calculator doesn't do fraction bars. And we've got a fraction bar there, you need the parentheses. So we're going to put that in the calculator. Find these test points. Clear it out. Put parentheses, x minus 1, close the parentheses, divided by parentheses, x plus 1. All right, and then we're going to hit second table. So at -2, our f of x is 3, and that's positive. And at 0, our f of x is -1, and that's negative. And at 2, our f of x is 0.33, repeating, or 1/3, and that's positive. So, we want positive sum brackets. We've already taken care of the brackets the way we put an open circle. Close. We want positive. We don't want negative. We want positive. So here's our solution set. It's minus infinity to minus 1, union square bracket 1 to infinity. Any questions? Okay. Just kind of making sense. Do you want to see the graph? Let's look at the graph. Let's see what it looks like. Oh, that's interesting. Look at that graph. So zoom 6. Let's see what that looks like. Oh, that's a little better. Okay. So it's a little harder to use the graph. This is a vertical asymptote at -1, and at 1 there's a hole. And so you can see the graph, I guess I can sketch it here. The graph really looks like this. Looks like this, with -1 being x equals -1 being a VA, and then it looks like it looks like it might have an HA at maybe 1. I don't know what value it's at, but it's something like this. Yeah, the horizontal asymptote, remember the rules for the horizontal asymptote? The horizontal asymptote at y equals 1 is because if you look at the simplified rational function, the degree of the numerator is 1, the degree of the denominator is 1, they're equal. So y equals the leading term, the leading coefficient of the numerator divided by the leading coefficient of the denominator. 1 over 1 is 1. So that's the graph. So it was positive from -infinity to -1 for x, and then it was negative until it got to 1, and 1 was right here, the 0. It was negative, and then it became positive. And that's the graph. Okay, last example for this. Okay, so this is more like a test problem. It's already set up. Single quotient and a 0 on the right. So you're just going to set the numerator equal to 0, minus x minus 3 equals 0, add 3, minus x equals 3, and then you want to make x positive, so if you divide by -1 on both sides, you get x equals -3. Now set the denominator equal to 0, x plus 2 equals 0, subtract 2, x equals -2. So the boundary points are -3 and -2. We have a less than or equal to 0, so where the denominator is equal to 0, that's a vertical asymptote we can't include. So we're going to use parentheses on this one.
How do you know if it's a vertical asymptote?
Well, it's a vertical asymptote because the function, nothing cancels. It's a whole if it cancels. But we found vertical asymptotes. Maybe did you miss that lecture? Did you watch that?
I watched Integrity.
Oh, okay. We found vertical asymptotes by setting denominators to 0 of rational functions.
Okay, and that'll always be...
Well, first we had to simplify the function. If anything canceled, if you had any factors that canceled, you can't cancel terms. So here you don't have any common factors. You have a factor in the numerator, minus x minus 3, and a factor in the denominator, x plus 2. So nothing cancels. So you set your simplified denominator to 0 to find vertical asymptotes. This would be a vertical asymptote.
So if it would have canceled, then it wouldn't have been.
Right, if it would have canceled, it wouldn't have been, and we probably wouldn't be working this problem. Okay. If it had canceled, it would have been a hole. We still couldn't let it be that value, but it would have been a hole. Okay, so, and then are we going to include, can we include the -3 here?
Yes.
Yes, we were going to include that, use brackets. So we always have to write these in order. So let's see, make this -3, and make this -2. -3 we're including, so we'll do a filled in circle. -2 we can't include, we'll make an open circle. This is our x-axis. And what I'm warning you about is on the concept, the vocabulary quiz for this section, it asks, it will show a number line with both of these filled in and ask for, and count it wrong if you use all parentheses. Okay, -3. Oh, wait a minute.
Let's see what.
That is not right. Minus infinity to -3, square bracket. That's the first interval.
Why would you use a square bracket on -3 but not 2? Is it because the vertical hole?
This, you never include setting, when, what the boundary point that you get when you set the denominator equal to 0, that would make the denominator equal to 0 and we can't divide by 0. So we never include those values, no matter if they're vertical asymptotes or holes. We can never include those boundary points. So we always use, so I put an open circle on -2 because that was found by setting the denominator to 0. Okay. And then the next interval is square bracket -3 to -2, parentheses. And then parentheses -2 to infinity, parentheses. Okay? So that quiz will ask you for the intervals. I think you put commas between them. And you do have to make sure you don't use square brackets on the infinities too. All right, so there's our test points. There's our intervals that it breaks it up into. I mean, no, those are our boundary points. Now we're going to figure out some test points to use, and then we're going to find f of x for those, or where f of x equals that. So test points. Something below -3, let's use -4. Here we're going to just use -2.5. And here I could use -1, but 0's in the interval. I just like to use 0. You don't have to. You can use -1. You can use +1. As long as it's in this interval, fine. Okay, now I type in my calculator y1 equals parentheses -x, -x -3, close the parentheses, divided by parentheses x plus 2. That's what I'm going to put in my calculator. Y equals parentheses negative x. You have to use the negative sign in front of the number, a term. -3, close the parentheses, divided by parentheses x plus 2, close the parentheses. Okay. We're going to hit second table. And we can read off at -4, we have -0.5, and that's negative. I never wrote what we were looking for, but we'll write that. So what are we looking for? Less than means negative, and we have some bracket. We already took care of those. So it's a good idea to just go ahead and write your intervals down. Then we'll be able to just pick the right one. Negative 2.5 is not on my table because I'm going by ones, but I can go ahead and look at the 0. The 0 is also negative with the value of negative 1.5, negative. Let's look at negative 2.5. So, if you go to second table set, you can choose to change your independent variables to x to ask. Don't change them both to ask. You're going to ask for x value. Second table, now our table's blank. And we can put in negative 4. We can put in negative 2.5. And we can put in 0. It lets you put in whatever you want. So at negative 2.5, f of x is 1, and that's positive. We're looking for negative, so we don't want this one. We want these two. So the solution is this union that. Minus infinity to minus 3 square bracket union minus 2 to infinity. Correct. That's our solution. Those are the x values that make that inequality true. Did that make sense? Very good. Then we have one more example, and we're done with this section. It's an example from physics. So, are you done writing? I think so. All right, so this is from physics, position functions. That's for a free-falling object is, goes by this formula, but it's minus 16 feet per second or something. Gravity, and they tell you all about it. S0 is the original height of the object in feet and initial velocity. But anyway, what we're doing is we're propelling an object straight up from the ground level with an initial velocity of 80 feet per second. And so that's why the initial velocity is here at 80. But we'll be able to use this. So its height at time t is modeled by this, where the height, s of t, is measured in feet, and the time t is measured in seconds. So here's what we're using. We're using s of t, which is the height, equals minus 16 t squared plus 80 t. It says, when will the object be more than 64 feet above the ground? Ground level will be where s of t equals 0. So we actually, more than 64 is greater than 64. Okay, so here's our inequality we're going to solve. So we're going to subtract the 64 first. And we're going to write it as minus 16t squared plus 80t minus 64 greater than 0. More than 64 feet above the ground means we had to subtract 64 here. That's the ground level. All right, so this is our inequality we're solving. This means that we want a positive values, and we're going to use parentheses on all the boundary points. If we write it in interval notation, maybe we want you just to write it in words, but okay. So it turns out that all of these numbers divide evenly by 16, and so we're going to factor out the negative 16. And so if you take negative 16 out of this, you get t squared, and you can do it in your calculator. 80,
It'll be 5.
yeah, 80 divided by negative 16 is negative 5, so you need a minus 5t. And if you divide negative 64 by negative 16, you get plus 4. And so you do want to look for a greatest common factor, and we're going to set this equal to 0. This is, we're going to find our boundary points. Let's get rid of the calculator here. So we find our boundary points. We set this to 0. So I already started factoring this. What does the minus 16 do? Nothing. We can just divide it out. It's gone. It doesn't have a t next to it, so we don't set that to 0 or anything. We can leave it there. It doesn't matter. So we're going to factor this, and this is a lot easier to factor than that. So always look for your greatest common factor. And so we'll have a t, and we're looking for the factors of 4 that add up to negative 5. That's 4 and 1. What do the signs have to be? They have to be both
Negative.
both negative. They have to be the same sign, and they're both negative because of this. So to figure out signs, if this is a positive sign here, it means that the factors have to be the same sign, but because the middle term's negative, they're both negative. But you can check to make sure it works. Always check your factoring. Factor to 0, t minus 4 equals 0. So t equals 4, or t minus 1 equals 0, so t equals 1. Alright, so those are the boundary points. We're not including the boundary points. We have to put these in order. 1 and 4. Open circles. So that breaks up our intervals into minus infinity to 1 and 1 to 4 and 4 to infinity. Okay, and then we can do test points. So let's use 0, 2, and 5. So I'm just going to make my y1 on my calculator is going to be equal to all of this. Just go back to your original thing. Don't use, in case you divided out the minus 16, don't use that. Just go back to your original thing if at all possible. Really. So y1, clear it out, equals negative 16, and you just have an x on the calculator. X squared plus 80x minus 64. And then we're going to look at our, let's change our table set back to automatic. Second table. At 0, let's go down a little bit more. Okay. At 0, we're at negative 64. So f of x is at negative 64. we're looking for positive, so we don't want that one. At 2, it's at 32, that's positive. And at 5, it's at negative 64, and that's negative. So, we don't want these. We do want that one. So the solution set in interval notation is 1 to 4. That means x is between 1 and 4. We can say, write it in words, the object is more than 64 feet above the ground from 1 to 4 seconds. Okay, so that's what it really means. Any questions? And that is section 2.7. And so because of the weather, I think we should quit. What do you guys think? I mean, do you want to stay? I mean, I don't care. If people want to stay, I'll go ahead and lecture the next thing. Or whatever you want to do.